Hello, my name is Caitlin Bache. I'm an assistant editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information to ASHRAE Journal readers and to others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by Mitsubishi Electric Trane HVAC. The subject is CO2 heat pump water heaters, all-electric commercial water heating for sustainable buildings. Today's speakers are Joe Cefaly and Matt Blocker. Joe provides engineering and application support for Mitsubishi Electric Trane HVAC US products, both commercial and residential. He's been with Mitsubishi Electric for 12 years, previously serving as a mechanical engineer in the Northeast. Joe is a lead accredited professional and certified energy manager. He earned a bachelor's degree in physics from Union College and his MBA from Northeastern University. Matt serves as the senior manager for commercial product development for Mitsubishi Electric Trane HVAC US. Having been with the company for 10 plus years, Matt has extensive experience with a multitude of VRF applications, most notably designing systems for cold climates. After serving as the commercial regional manager for the Central Business Unit, he transitioned to the product planning and development team 4 years ago. He holds a bachelor's degree in mechanical engineering from the Illinois Institute of Technology. Matt, the microphone is all yours.
Thank you very much. So today we're going to look at just our overall learning objective is looking at domestic hot water and the overall demand for an alternative solution to today's traditional approaches of using fossil fuels for generation of hot water. So at the end of this, what we're trying to convey is the ability to understand some of the demand and incentives that there is for these products on the marketplace, describe the basic components and what goes into this CO2-based hot water heat pump, and then really look at what different applications can benefit from it and where we're seeing the strong initial pushes in the marketplace today. And then at the end, also understand that there are some differences between this product and traditional systems out there. So want to make sure we have everybody engaged as needed to make sure these projects go out without a flaw or hitch. So first, when we looked at, as an industry, looked at any commercial buildings, we look at where are our potential for electrification, reduction in greenhouse emissions, things like that. And obviously, we all first started with, in commercial buildings, space heating, space cooling in the building. And there's many products out there in the marketplace, like VRF and others, that can serve that purpose. And once we look next, one of the next biggest buckets, so to speak, of opportunity for removal or replacement of natural fossil fuel type products is the domestic hot water segment. So if you look at the U.S. Right now, it's estimated that our water heater energy usage is responsible for emitting about 100 million tons of carbon into the atmosphere every year. And that's really what the problem statement we're trying to help with this product is to give end users and different implementers throughout the marketplace another solution to that problem statement. If you look at today, there's already several initiatives out there, including New York City Local Law 97, 154, Seattle Energy Code, and then also many that are coming up to speed with this concept of how do we get rid of carbon emissions in our commercial buildings. So right now there's already legislation in place that's helped push towards this, and whether it's a prohibition of use of fossil fuels in the building or different penalties imposed on using fossil fuels, there is a lot of movement towards this, and it doesn't just align with just these couple areas, but very heavily in both the Northeast and West Coast jurisdictions to get towards some more renewable solutions and Beyond this, what we're going to see is more routes and pushes from different utilities and implementers to also help this transition towards non-fossil fuel type heat pump system. So if we look at what the product is, it's really made for higher volume domestic hot water usage facilities. So if you look at our core applications that we're really focusing on today, it's been multifamily, senior living, and hospitality hotels. And also, we can see it in any application out there. So higher ed, K through 12, campuses, kitchens, laundry. It really is a wide fit product, but we're focusing right now on a lot of those higher use rates for our commercial buildings out there today. So what is it? What does it look like? So on the right here, you can see a picture of our CO2 hot water heat pump. And we'll go into some of the details of this, but what we've done is over the years in the global marketplace have looked at different ways to accomplish this, and we have various products throughout that have been launched globally, and now we're looking to launch this CO2-based version, which is really the best solution for serving domestic hot water and bringing that low water temp up to storage water temps at a very good COP and efficiency. So when we look at this, the real overall goal is, trying to get a product or solution out to the market that can remove the need for fossil fuels in a building. And that's really what a lot of those legislation and rules are surrounding on. With that, just one of the natural benefits of CO2 refrigeration is that we have really an ozone depletion potential of 0 and a GWP of 1 for that refrigerant type. So while it's actually the best refrigerant type for this type of solution, it also just actually adds those natural benefits of being a natural refrigerant and having very little environmental impacts to our world here. So so I'll look into this a little bit closer, but this is kind of one of the cores of our technology compared to other traditional systems out there is the ability of a single pass heat pump system. So what I mean by single pass is that what we're going to do is take the cold city water temp and take it from, let's just say 50 degrees and raise it all the way up to our storage temperature, 140, 150 degrees or higher as needed. And we do that in one pass through this spiral tube heat exchanger, which is a patented heat exchanger that we have on the marketplace. And one of the big benefits of this is being able to use the CO2 refrigerant cycle to keep high efficiencies up in doing that high delta T on the water throughout the system. So with that, and also the fact that it's CO2 based, we're able to do really high hot water temperatures compared to a lot of traditional HFC products. So we can do up to 176 degree water leaving the heat pump. And we can do that all the way down to negative temperatures out in the marketplace. So we rate the product of -13, but can actually run all the way down to -35, which is one of the big benefits of using CO2 as a product. And paired with that, we also use a lot of our technologies that we have today in our VRF product of having the inverter compressor and flash injection like you would see on our hyperheat products to further improve that heating performance and COP at low ambient conditions. And that's really, when you look at a lot of the products, that's really one of the big differentiators is how well we can perform at low ambient conditions for the product market. So with that, there are some changes, though, when you look at the marketplace today. It isn't going to be a drop-in-place replacement for a boiler or a hot water heater today. And it does take some things throughout the system to make sure we can achieve those high efficiencies on the system. So I'll call out a couple of those major components in the system, and then we'll let others speak on a little bit how they interact more. So on the left here, you can see we have the CO2 hot water heat pump. And in that heat pump has that heat exchanger compressor and also a small circulator pump that would then serve what we call a secondary heat exchanger. And really what the secondary heat exchanger is for is to give you separation from the potable water, but also give you an easy spot to be able to service and maintain the system so that if you were to have poor water quality or fouling over time, that you could easily clean that heat exchanger versus having to work on the heat exchanger within the heat pump itself, being CO2 on the other side. So next is we have our storage tanks. So one of the big keys of this compared to traditional storage tanks is making sure we can keep good stratification in the tanks. So you'll see any of the inlets and outlets of the storage tanks are going to have what we'll call sparge fittings or baffles to essentially redirect that incoming water flow in a perpendicular nature and also slow that flow down so you can keep good stratification in the tank. Because one of the really big keys to this system is being able to get cold water back to the heat pump. That's what it likes to see, and that's where it's going to run most efficient. Next is a swing or maintenance tank on the far right here you can see, and this is really what we're using to take care of our recirculation load in the building. So most, or if not all, commercial buildings today have hot water recirculation to give better response time to the space. And what this swing tank is set up to do is just maintain that load on the system. And what we've kind of put together for the marketplace is a full package of all these different components, as well as a control offering to be able to, make this as easy to implement into the marketplace as possible. So I'll hold it there and let introduce over to Joe here to talk some more about some of the benefits of the hot water heat pump. And he'll also talk about a little bit more of the flow through these different components.
Great, thanks, Matt. During today's webinar, I'm going to talk about the benefits of utilizing CO2-based heat pump water heaters, as well as some design considerations. Then I'm going to pass it back to Matt to walk through a case study, and we'll follow up with a Q&A session at the end here. So Matt had already mentioned, but CO2-based systems have a ozone depletion potential of 0 and a global warming potential of 1. CO2 is the basis of the scale for GWP, as all other refrigerant types are compared against this baseline. Using CO2-based domestic hot water systems allows you to electrify your building, and these systems actually get greener with time as the utilities add more renewables to their electricity generation portfolio, which is fueling the system. In comparison, natural gas domestic hot water systems will only get less environmentally friendly with time as the system ages. As compared to an all-electric water heater, CO2-based domestic hot water systems offer up to 4.5 times this efficiency. Blended or seasonal efficiencies will vary with the ASHRAE climate zone for the installation location and other factors, but the end result will inevitably be multiple times the efficiency of an electric water heater. Several cities and states across the country have mandated all-electric domestic hot water solutions for new construction, and some of them also apply to retrofit applications. Many of these jurisdictions offer incentives to offset the first cost of implementing a heat pump water heater solution. And after the hurdle of first cost has been crossed, operating cost is similar to that of a gas-fired domestic hot water system, and sometimes even less. I saw in the question thread here the cost. There is a premium to upgrade to a heat pump water heater system. So there's definitely a first cost premium as compared to gas. But as it's being mandated across the country, I guess there just aren't really other options. Some CO2-based heat pump water heater systems utilize specialized compressors that include flash injection, which is an auxiliary cooling circuit that allows the compressor to achieve higher compressor speeds at low ambient conditions without risking damage to the system, thereby achieving higher lift and more BTUs per hour than other inverter scroll compressor-based systems. Some manufacturers can achieve 100% of nameplate heating capacity at 36 degrees Fahrenheit ambient, and 50% of nameplate heating capacity at negative 13 degrees outdoor ambient conditions. This allows the heat pump water heater to produce 176-degree domestic hot water at negative 13 degrees Fahrenheit, but just at a reduced GPM. So the sizing of your storage tanks becomes important in your system sizing, as there needs to be enough storage capacity during drawdown events and enough production capacity during periods of latency. Oversizing of the heat pump water heater system will cause excessive cycling and diminished COP. The average commercial heat pump water heater is around 10 tons in capacity, which, depending upon climate, is suitable to serve 40 to 70 apartments, hotel rooms, and so on. It varies with the climate and other factors such as storage sizing and storage temperature. If an application requires more capacity, you simply add more modules to scale capacity at the heat pump water heater domestic hot water plant, and you also have to increase the size of your storage in lockstep. Let's now transition to heat pump water heater system design considerations. Matt showed a similar diagram earlier, and I'm going to go into a little bit more detail here. The commercial heat pump water heaters get installed outside to reject cold air to ambient. From there, it's cold return water back to the hot water heat pump and hot supply water out to the building. Many systems utilize a primary-secondary setup like is shown in the diagram, where the hot water from the hot water heat pump circulates in a closed loop through a secondary heat exchanger. This is typically done to protect the heat exchanger inside the hot water heat pump, since the secondary heat exchanger is relatively inexpensive. There is a secondary pump on the other side of the heat exchanger to circulate domestic hot water to the storage tanks. The storage tanks contain sparge systems that reduce the water velocity to 4 feet per minute or below in order to get good stratification in the tanks, so that the return water to the hot water heat pump is as cold as possible, which maximizes your COP efficiency for the system. From the storage tanks, the domestic hot water goes out to the swing tank, from where it travels out to the three-way mixing valve and out to the plumbing fixtures in the building. The purpose of the swing tank is for loop maintenance inside the building, so that when there's no load, no recent drawdown event, and the hot water heat pump is off, so that the fixtures in the building can still receive hot water quickly, and the water inside the extensive hydronic piping network does not get stagnant. ASHRAE recommends setting these storage tanks to 140 degrees Fahrenheit to prevent Legionella, and the swing tank at 120 degrees Fahrenheit in order to maximize COP, so that the swing tank's electric element has minimal runtime. Heat pump water heater design is significantly different than gas-fired domestic hot water systems. The general rule of thumb is to reduce the BTUs per hour production to 1/3 of how you would size a gas-fired system, and increase the storage capacity to 3 times that of a gas-fired system. Controls overlays include demand response and COP averaging, giving a seasonal performance average for how the system operated. As mentioned previously, the heat pump water heater processes the incoming city's cold water, while the swing tank is handling the building's recirculation water. During hot water production, the system can feed high temperature water to the swing tank, which also mixes with the warm water, recirculation water. Water within the swing tank is maintained within a specified temperature range, for example, 120 to 125. The swing tank typically includes a control panel with 3 electric heating elements for temperature maintenance. The heat pump water heater should be installed outdoors at a minimum of 1 foot away from any adjacent building, according to most manufacturers. 3 foot in front is the required clearance on the front side of the unit that contains the high voltage electrical in and electrical disconnect per NEC National Electric Code. For cold climate markets, the primary side of the heat pump water heater system should include food-grade propylene glycol to act as an inhibitor, but also to prevent against freezing, although heat tracing from the heat pump water heater to the inside of the building is also strongly recommended. Equipment maintenance is minimal for heat pump water heaters. There's a strainer on the water intake side of the heat pump water heater, which should be installed in a manner that makes it serviceable. The condenser coil should be cleaned annually or as needed. You're going to want to back flush the secondary heat exchanger that separates the primary side from the secondary side. The heat exchanger should be installed with connections for flush in place type of maintenance. The maintenance interval is going to vary with water quality, and so that's going to be drastically different from region to region. There's anodes in the storage tanks that should be checked and cleaned every 6 months. Should their diameter reduce by 20% or more, they should be replaced. These sacrificial anodes prevent rapid failure of water tanks due to electrolysis. Should the coil on the heat pump water heater collect dust, debris, it should be cleaned like a standard condensing unit. Cleaning interval will vary with air quality, installation location, and so on. If using propylene glycol on the primary side, it needs to be supplemented over time as it degrades and requires makeup. Expansion tanks can sometimes be a point of failure as the internal bladder can fail, especially if there is an overpressurization event. The system can be integrated into a building management system, BMS, BAS, through a local area network or BACnet interface. Local users can monitor and control operation, modes, set points, and tank temperatures. There is demand response capability. Systems can preload tanks with hot water prior to a demand response event, giving tenants uninterrupted access to hot water. Primary thermal storage tanks and swing tanks allow the system to handle a higher peak demand. And with that, I'm going to pass it back to Matt to go through a case study before our Q&A.
Perfect. Thanks, Joe. Yes, we have 2 different case studies we'll show here, and we could talk about a little bit more in the Q&A as well. But the first case study is actually the first installed pilot project for this several years ago at Bayview Tower. And this is in Seattle, Washington. And looking at it, it was a 100-unit low-income multifamily housing, existing retrofit project. And existing in the building was all-electric water heaters. So the whole entire building was based on electric water heaters. And what we kind of developed and went through with various industry partners is a method to add a QHV heat pump onto this project and include it as an easy changeover from their existing system. So this isn't necessarily an offering that we're promoting today, but is a solution we provided for this system. So what this looks like is we had a 1 heat pump, again, about a 10-ton heat pump. And then in this pre-manufactured offsite assembly, we had 3 storage tanks and pumps, heat exchangers, as well as our controls to control everything. And essentially it meant 2 water tie-ins to their existing hot water system. So as you saw before, what we ended up doing for this project is leaving all the electric boilers in place or water heaters in place, and they act as that swing tank or regeneration for your recirc load. And then this is basically just our storage volume for the system. So even at 100 apartments, we can serve it with 1 heat pump in this scenario. And with this, we're doing a lot of extensive monitoring and things throughout the system to monitor COP, which has been very good, very high so far. And we are also implementing and using it as a research site to help different utilities implement demand response with these systems. So this system is using demand response today and getting that signal from SkyCentric's module from the utility company. So just looking at it, high-level numbers, we're expected, and we're still kind of flushing out some of these numbers as well, but expected to drop over 50% in kWh per year for this building, and which makes a lot of sense, being that it was all electric prior, going to a heat pump-based solution. And also looking at seeing the rebates being very generous for this one, which helps drive these initiatives forward. But overall, for the end user, about a $15,000 annual building cost reduction for operating costs. So really, really large impact and very successful story for this project, and using it to kind of build on and create better solutions for future projects out there. So the next case study is one of our first projects on the East Coast, and it's in Connecticut, and it's called Hotel Marcel. And a very cool looking building that is actually an old tire manufacturer building. It was bought and turned into a boutique hotel. And so if you look at the building, it's kind of got split up into two different portions. The bottom portion here is kind of the common areas and conference rooms, things like that. And the upper portion is all hotel rooms now. So with this, it's, kind of historic rehab in that iconic landmark district, and very, cool retrofit to take this from, an older, office building and change it to a hotel. And they're actually trying to achieve net zero for the entire building, which would be the first net zero hotel in the U.S. So what we have for this whole building is it's actually built up of 3 hot water heat pumps. So it's just a picture of one installed up on the roof. It has control package and all those different accessories that we talked about, storage tanks and swing tanks and pumps, heat exchangers. But it's split up into 2 separate systems. So one system serves the hotel rooms, and the other system serves more of those common areas throughout the system. So it's 2 overall hydronic systems. And with this, they do think that along with the VRF and controls and also some of the energy efficient equipment elsewhere on the project, ventilation and things like that, that they'll be able to achieve being the first net zero hotel in the U.S. So it would be a very big statement, being that, a hotel is very hard to achieve that on in general. So if you look at this overall, and some of the kind of the key takeaways is that, there are now products in the marketplace that can achieve hot water production for air to water heat pumps, even at cold climate. So again, down to the -13 or below range, which covers a large amount of our U.S. marketplace. And there's a lot of things that go into play and a lot of differences from our traditional, gas-fired type products out in the marketplace. But with good collaboration, working with everybody on the call and different partners in the industry, we can make this transition smooth and get to a good solution for the marketplace moving forward. So with that, we do have some additional resources here that we'll be able to view and send out, but I think we can jump into some of the Q&A sessions for the presentation.
All right, that sounds great. Thank you, Matt. Thank you, Joe. And thank you to everyone who submitted a question. Let's get right into it. Now, here's a question that several of our audience members have asked. Can this sort of system be used to heat a swimming pool?
Yeah. Thanks, Andy. So I'll take that one. Technically, technically could, but your efficiency would not be good. So we will have other products coming into the marketplace that will be better suited for that, because that is typically more of a low delta T approach. So this product specifically is made only for domestic hot water, and that's where we kind of achieve the best efficiency, is having that high delta T or high lift on the system.
All right. Do you want to add anything, or Joe, or move on to the next?
Yeah, just expanding on that. Like Matt said, this product is purpose-built for domestic hot water, and it really wants to see a really high delta T single pass. We have us and other competitors are having products that will come to market that are multi-pass low delta T, and they'd be way more suitable for that type of application.
All right. So we've also had a few people ask about recirculation in the building. And specifically, is the swing tank needed if there is no recirculation in the building?
So I guess I'll tackle that one. If you don't have recirculation in the building, then no. You wouldn't need the swing tank, but anytime you do have recirculation, we want it there so that we don't get mixing back in the main storage tanks, which would then greatly decrease the overall efficiency of the heat pump system. So, but if you didn't have recirc in the building, you could do it without the swing tank.
Okay. Jeff, do you want to add anything, or can I move to the next?
Yeah, I think it's really dependent on building size. If it's a large hotel, you don't want it to take 20, 30 minutes for the shower to get warm if you didn't have the recirc loop. And so that's where it's really critical to have the swing tank, so that there's that maintenance loop that, you're not having a huge delay in getting your domestic hot water.
Great. All right, here's another question from several audience members. Can the heat pump be installed indoors?
Currently, no. There's not enough external static pressure on the condenser fan of the heat pump water heater to duct it out. You could potentially do it, but you'd need an auxiliary fan for ventilation just so that you're getting the right CFM across the coil. But as of right now, most manufacturers are not recommending it because it just doesn't have the condenser fan external static pressure.
All right. Matt, if you want to, is there anything you want to add to that, or shall we move on to the next? All right. So, does this system use a double wall heat exchanger for the secondary heat exchanger? That's another question. It's come up a few times.
It will in the future. Unfortunately, most of the manufacturers, supply chain issues, the lead time is really long. And so from a code perspective and from a safety perspective, we've just been promoting that you use food-grade propylene glycol on the primary loop, and that you keep the secondary loop pressure higher than the primary side, so it's pushing in that direction. And so right now we're using single wall. Some manufacturers are using double wall, but accessibility to those components has been difficult in recent history here.
Gotcha. All right.
Yeah.
Matt, anything you want to add?
Just to add to that, the heat exchanger, that spiral tube gas cooler in the heat pump itself, is technically a double wall heat exchanger as well. It just is, so we're kind of adding even another layer of protection on it, but we're really using that secondary heat exchanger for an ease of serviceability and ease of cleaning, things like that within the system for overall longevity of the system.
All right. Okay, so there are a few questions with regard to the inlet temperatures. So, for example, colder climates have lower incoming water temperatures. So what sorts of sensitivity and hard thresholds do you have on inlet temperatures?
Yeah, so basically, summer temperatures all the way down to -13 Fahrenheit, we're going to be able to produce 176-degree hot water on the primary side. And all that happens is the integral pump inside the unit, the water pump, it's going to adjust the GPM so that it has enough capacity to make that 176, because the water temperature is more important than the amount of water coming out of it. So that's basically how it's working right now.
And
Matt, do you want?
The actual threshold for lower end entering water would be 41 to the heat pump. So one of the advantages of having that secondary heat exchanger in some ways for, if you were to drop below that for your city water temp in say an ultra low climate, you would still be seeing, well above that 41 at the heat pump, allowing it to still run for that cold water inlet. So.
All right. So does this system require heat trace on the outside piping, and would electric resistance be required as emergency backup?
So a couple of things we've done is it's always good to have heat trace in a cold climate, just in case. There is the pump will circulate based upon cold climate. Like, it knows that there's a risk of freezing, and so it'll just start circulating water when there's no demand and the heat pump water heater is not working. But the heat trace is always just a good second layer of. It's relatively inexpensive, and then you got peace of mind that you're not going to have a freeze up piping situation.
Okay. Add anything you want to add on?
Yeah, to touch on that, if we are in a cold climate that's going to get below freezing, that kind of thing, we are starting to recommend using propylene glycol on that primary loop to prevent any kind of damage. But if you don't, you can also still use the heat trace method, but it would be good to try to get that heat trace at minimal on UPS, to be able to ride through any kind of power outage, thing like that, on the system. But not always available on all commercial buildings, so that's why we kind of have both offerings out there for either the heat trace or glycol solution.
Well, speaking of glycol, what is the maximum allowable run from the heat pump to the heat exchanger on the primary loop with the glycol or heat trace?
Our factory currently has approved 30% propylene glycol. However, we're revisiting that for 40%, as 30% only gets you to 8 to 10 Fahrenheit for production. And there's minimal D rate too.
Yeah, and the overall distance of that primary pump that's built into the unit to that secondary heat exchanger is about 195 feet. One direction, so including all different hydronic components and everything in that primary side loop.
All right. So this next question is about controls. So if we talk about integrating the system into a building management system, does this mean the entire system has a controller that controls the heat pump, secondary pump, tanks, swing tanks, and any other components, or is the integration just with the heat pump itself?
Yeah, so
now, on that one,
one of the things early on we wanted to do is provide a solution that is an all package in one. So if you have a BMS on the project, we can definitely integrate into it. But even if you have don't have a BMS on a multifamily project or something, you would still have this a full control panel provided by us that would integrate all those different components, monitor, calculate out performance and everything, and also it is brought with our solution to a cloud-based interface as well. So if you had, because it's a little bit more of a technical system, you would have that remote monitoring capability and be able to actually see true performance of the system, even if you don't have a BMS on the overall project. So that is something we're including with all projects out of the gate.
All right. Joe, do you have anything you want to add?
Nope. All good.
All right. So are there any additional certifications or best practices required for working with the extremely elevated pressure that using the CO2 as a refrigerant might require?
Yeah, the working is up to 1,600 psi, Matt, and then so the equipment is tested to 2,000 psi for safety reasons to have a little bit of margin of error in there. And really, this type of equipment, it's more likely that the service route that it's going to go is that you're going to just swap them out like you would a PTAC in a hotel room, that like you'll take it off site to a dedicated party for servicing rather than servicing it on site.
Yeah, and I know it's a little bit outside of our normal HVAC trends, but there are plenty of CO2-based companies out there that do refrigeration work, rack work, things like that for supermarkets that are all capable to do the work on this equipment. And one of the reasons, or one of the things we're pushed for early on is having some redundancy in N+1 in the system design. So like Joe said, if you had, something ever did fail, you could isolate that system and either pull it out to do the work off-site or do the work on-site with qualified tech. So, as far as, certifications, anything like that, there really is just the same as you'd have to work on any other CO2-based piece of equipment.
Okay. Let's talk about sizing. So how do we size the heat exchanger and the heat pump?
It's typically all going to be done by the manufacturer because they kind of go in lockstep. If you had it, sized externally by someone else, that's why we're actually providing a package solution here. Just because, it is critical to get the heat exchanger sized appropriately with the heat pump and whatnot. And so right now, most manufacturers are providing a package solution that includes the heat exchanger, the pump, and so on.
All right. Anything you want to add?
No, it's good.
All right. Okay, next question. So when stacking the heat pump water heater on the primary side, is it recommended to go parallel or series?
We would always want it to be in parallel because we always want that same cold water coming back to each one of the heat pumps. So it would always be in parallel in that nature, so you're not, tripping out the heat pump from, previous one bringing heat to it.
Okay. Anything you want to add?
Nope, all good.
Oh, all right. Is this system UL listed?
Yep, it is UL listed to 60335 2-40.
All right. We can move on to the next one there then. Is the secondary heat exchanger a part of the package system, or is it a separate piece of equipment?
Right now, we're actually doing a parts and pieces method where you've got a secondary pump, you've got a secondary heat exchanger, you've got temperature sensors. There's a lot of components. Because of that complexity, manufacturers like us are moving towards a intermediate skid. So you'd have two pipes from the heat pump to the skid, two pipes out to the tank, and then from there it's to your three-way valve and to your fixtures.
All right. Anything you want to add?
No, I guess just the point of, when we're looking at this because of a lot of those complexities, we're, kind of full hands-on as to helping project manage it and make sure everything does get installed right. So that is really our goal in this, is to, end up with good, clean projects that are working well and meeting the efficiencies we target.
All right. Can the swing tank be heated with a secondary CO2 heat pump?
I'll answer that one. So we will have other provisions of other heat pumps that will be better suited for that in the future, but it would not likely be a CO2-based heat pump just because of the natural low delta T that you would want on that swing tank. Just kind of doing that maintenance load, we would likely provide more of a multi-pass style heat pump that would more than likely be a HFC-based refrigerant with a similar low GWP refrigerant.
Okay. Let's move to the next. So in warmer climates, can the secondary heat exchanger be eliminated and domestic water run through the internal refrigerant to the water heat exchanger?
The problem with that is that the secondary heat exchanger is about a $500 to $600 heat exchanger, and you wouldn't want to compromise the cost and complexity of the heat pump water heater itself. And that's why there's the primary secondary loop, is that you wouldn't want to risk the integrity if you had bad water quality. So yes, is it possible? Sure, but it's risky.
Yeah, and just for now, we're not going to allow that removal of the secondary heat exchanger, regardless of the climate, just to make sure we get longevity out of the systems overall.
Gotcha. Another question about ratings. Is the system NSF rated?
So if you look at that specific heat exchanger in the QHV itself is not NSF rated to date, and one of the reasons why we wouldn't go directly to it as well. But all the other components throughout the system are going to have that rating that require it. Some would not require it, but the pumps, the heat exchangers, and things like that would require NSF rating to comply with it.
Okay. If there's a power failure, does the CO2 in the system need to be recharged?
No, the CO2 in the heat pump itself is a closed system, so if you lose power, it's just going to, turn the compressor and fan off and, kind of sit idle until power's reapplied, and then it would go through its initiation kind of startup process again, and run without a hitch from there.
And the biggest concern it would be if you lost power in a cold climate and you froze some pipes, like if you weren't circulating because the heat trace was off, or the pump inside the heat pump water heater couldn't circulate water. That would be the biggest concern.
Okay. We have a few questions concerning alternative uses for the system, so I'll just combine them. So can the heat pump be used for comfort cooling while providing domestic hot water, and is it possible to also do space heating with the system?
No, but there's a product coming in the very near future that will do that kind of thing. I'm sure multiple manufacturers will have it, and basically that's your multi-pass low delta T that you can do radiant floor, you can do space heating, that sort of thing. This product was purpose-built for domestic hot water, and so it's a super low GPM, high delta T single pass.
All right.
Yeah. What I guess I would add to that potentially, and Joe's correct on all points there, is, when this thing is generating hot water, it is discharging pretty cold air off the discharge. So there may be some opportunities to recover that cold air for other cooling purposes, if you can account for the different fan statics and things like that. So we haven't done that to date, but there could be some potential there for certain applications.
Great. How much turn down does the system have?
So I'll answer this one. So the system does have variable speed compressor, ECM condenser fan, everything like that, and the turn down is into the single digit or double digit, 10 to 15% overall. but the system actually won't operate like that. So it's going to operate more as a storage-based system where it's going to use those inverter compressors and fans as a soft start mechanism. But beyond that, it's going to run at close to 100% load at all times until you get your storage volume up to temp in the tanks, and then it will shut off. So it doesn't act as similarly to a VRF, say, condensing unit where it's always modulating to match the load. It's really just trying to, build up that hot water temperature in the tanks. And once it's achieved that, it's going to, cycle off and wait for the next drawdown effect through the tanks.
All right. So I'm going to combine a few questions because a lot of people have asked this. Is this technology available for small applications, such as smaller office buildings and maybe even single-family residences?
I think some manufacturers have products. It's going to vary by manufacturer, but our current offering is just basically you need 50 hotel rooms or 50 residences, multifamily, to warrant a single system. However, we and others are bringing stuff to market that's more in the not single family home, but 10 to 12 residences.
Anything you want to add?
Yeah, it's to the future, I guess. This is a 40 kW product, and there will be another more light commercial product down the road, into the 7.5 kW range, to tackle some of those smaller light commercial or smaller multifamily type buildings.
All right. Oh, so this is a different question. So what are the typical COPs when using this product in mild outdoor air temperatures, such as 47 degrees Fahrenheit?
Yeah, so COP can range, drastically as obviously with ambient temperature, but, in a milder temp, you're going to see anywhere from 3.5 to all the way up to about 4.5 for a COP out of the product. And then as you get lower, that is one of the benefits of CO2 is it can maintain a little bit higher COP into those lower ambient temps. So you can see the 1.5 to COP even at 0 to negative conditions.
Okay. Any additional thoughts?
Nope.
All right. So is it possible to integrate the system with an existing gas boiler hot water heater? Is it possible for the two systems to work together seamlessly?
Matt, I'll let you take that one. You've had more experience in that regard.
Yeah, so it definitely is an opportunity, and the easy button would be to utilize the existing gas water or even new gas system for that swing tank usage, and then you would use the hot water heat pump to do a lot of your generation work as much as possible. So, we do have examples of that where, people want to use either both fuels or they still want to kind of test the water with this to say, hey, we're not ready to jump in 100%, but, we want to peel some of the load off our building, from gas use, and we've done that in some cases already today.
Okay. All right. So for the primary propylene glycol loop, is an external thermal expansion tank required, or is there one already integrated, already in the heat pump?
It's external. Both on primary and secondary side, it's external.
Yeah, so on the primary side, we'll always try to keep a minimum, actual volume of fluid of a little over 10.5 gallons. And then depending on your pipe length and things, that might require a buffer tank small little buffer tank, but we would also have that expansion tank to cover that, as well as your expansion tank on the secondary side that would cover your whole building, water volume, so to speak.
Okay. So how is defrosting for the outdoor coil done?
Yeah, so I can handle this one, but so defrost is a little bit different than maybe what you've seen in others, but we don't use like electric heat or anything like that to defrost the coil. What we will do is reroute the refrigerant in the internal to the condensing unit and use a hot gas defrost to defrost the coil quickly and then go back into heater operation. And when you're in that defrost, what it's going to do is it's going to actually stop the water pump and flow of water to your storage tanks so that you're not then pulling any heat or sending any cold water back to the heat, to your indoor storage tanks. So think of it like, when it goes into defrost, you're just getting to, stop producing capacity for, 5 to 7 minutes and then return into normal mode and go back to generating heat very quickly. So, I think one of the questions I saw as well as scrolling through is from a standby state, for it to take it from 50 degrees to 170 or 150, whatever you have for your primary set point, it's going to do that in under a few minutes. So it's a very quick response time as far as getting up to that temperature from an off state or from a defrost state.
Okay, sounds good. Joe, anything you want to add?
Nope, I think that was thorough.
All right, great. Okay, so will the CO2 in the system degrade over time? Will the unit need the CO2 recharged at some point?
Yeah, so the CO2, since it is a closed loop system, there is, no, as long as there's no leak or anything on the system, it will not degrade over time. So that, just like any HFC refrigerant out there, as long as, it's closed and you don't have any kind of other outside influences, you will not have to recharge it or adjust things over time.
All right. Closing in toward the end, so I'm going to try to get in maybe one or two. So will multiple heat pump units be piped to a single secondary heat exchanger?
It's a one-to-one relationship right now, and what it does is it makes the project repeatable, reliable, and we can guarantee the performance. And so right now it's one heat pump to one heat exchanger to one pump, and you just scale it as necessary.
All right. Since the water is isolated with heat exchangers, could the closed water loop contain antifreeze?
Yeah, that would be the same as on your primary loop could also, contain antifreeze or propylene glycol.
All right. Final question. Are there any incentives that might be available for offsetting the cost, or could this product help with qualifying for any other efficiency or sustainability related benefits?
Absolutely, and we can share with the everyone that was on the call today or that registered. We can share that. We have a utilities department that handles that sort of stuff, and so we would first check with them, and then we can send out like a list around the country.
Yeah, and the incentives are really, to date, are really more locally based. So local jurisdictions are really, pushing that, and local utilities or implementers. So some will have incentives to go to, a heat pump hot water heater. Others have even clear-cut incentives to go just to CO2 for refrigerant. So they vary pretty widely from market to market. But as we see more and more of it, I think we'll get closer to a consistency across the U.S. marketplace.
Perfect. All right. Well, we hit 3 o'clock exactly. So thank you, Matt. Thank you, Joe. Thank you to everyone who submitted a question. Thank you, and thank you to ASHRAE for this webinar, and we'll catch you next time. Hope you learned a lot.
Thank you, everyone. Appreciate it.
Thank you.
You guys did fantastic.